All right. Hi. Just wanted to confirm if you can hear me.
Yes, we can.
Okay. All right. Great. Thank you
Yes,
very
sir.
much. Okay. So let me see if downloading is still here. So oh, this is interesting. Sorry, just give me a second. Okay. All right. This is good stuff, I think. So just give me a second. Let me just, I seem to have the wrong file downloaded here. So let me just redo this just to make sure that I'm doing the right thing here. So as I'm fidgeting around here, I just wanted to find out if people have any specific questions with regards to what we covered the last time we met. Just wanted to start out by, I know I sent out an email, but I wanted to start out by apologizing for not making it, was it Monday, I think? If I'm losing track of time here, I think on Monday, couldn't make it. We will have a makeup class. We actually have sessions this coming weekend, so Saturday and Sunday, and then the other weekend as well. So I'm sure we'll be able to catch up. But I just wanted to find out if people have any specific questions with regards to the things that we did on, I'm not sure if it's, was that, I don't know when last we met, was that Saturday or something? Where we were looking at, we're still looking at number conversions essentially anyway, but not sure if people have any specific questions with regards to that. If not, which appears to be the case, then I'll just share my screen and then we can start. Now, there's something really interesting happening with Google Meet, right? They keep rolling out these nifty features, which is pretty nice actually. This tool is becoming comparable to some of the well-established software tools for video conferencing that are specific to teaching and learning. Now, I just discovered, right, when I was just sharing my screen, that when I was recording, actually, that there's this new feature called Whiteboard, right? I think it's integration with Jamboard, right? Never used it before, but this is nice. Also, I was reading up a blog not too long ago about how Google now automatically send through, is it an attendance report, right? So previously it was very difficult for like an instructor to ascertain or to try and figure out who exactly is attending class. I mean, not that it matters in our case, but for courses where it matters, where attendance is extremely important, right? Where you get credit for attending. What they're going to start doing, I don't know if they've started rolling this out yet, but they will be sending through attendance reports. So showcasing exactly how long a student or a participant was a part of the meeting, what time they actually attended the meeting, which is quite interesting actually. It might just enable people to pull out very interesting statistics. But if there are no questions, then we proceed. We're still lecture series number 14. So we're getting to a stage where we discuss conversion from decimal to hexadecimal and the reverse hexadecimal to decimal. Hopefully you've gotten a chance to play around with some of the examples or problems that are actually in these slides. Right? Before we start, just a few announcements. I wanted to start by, my God, we were looking at the results for quiz number 11. This was a bit of a shocker here, right? Not sure what's happening here. I don't know if it's people just not being serious here. But out of the 67 people that attempted the quiz, right? We're thinning the head now. So this is a snapshot. Only 13 out of the 67 actually got 4.5 and above, right? So in essence, less than 20% of the class passed the quiz, or less than 20% of those that attempted the quiz ended up passing the quiz. Very, very sad. Yes?
For the question in regards to the quiz.
Okay.
I answered the quiz, but it showed I never submitted.
That's a query session. You send out an email. If you have sent out an email, I will respond.
Okay.
Yeah. If you have any problem, I mean, we've gone through this before. If you have any problem with regards to how you were graded, if you feel you got the answer right, but it wasn't, you weren't allocated the full marks, you reach out, right? The query session is easy. You send out an email, you explain exactly what the problem is, and then there'll be back and forth, and then we'll fix the problem. All right. I hope the snapshot will change once people do that. But right now, as things stand, this is it here, right? This is the sad or the sorry snapshot of quiz number 11. I don't understand. I really don't understand what was so hard about the quiz, right? Somebody asks you a question. Is it true or false that for you, is it mandatory that you are supposed to format a storage medium before you back up data on it? Really? True? Really? You know, is it mandatory that you're supposed to petition it? The vast majority of you are just saying true. You did not understand what we talked about. And I know why you did not understand what we talked about. You know why? Because you did not read. You're not reading, you're not studying, you're not playing back those video recordings that are being shared, right? Don't know why you've decided to do that, right? Don't know why you've chosen that very unfortunate path, right? We know you're not doing this, right? And we'll show you that you're not doing this. We know, right? If you think that you'll be able to just see this, no, we know that people are not studying, and we know that you're not studying because we can see the stats on Moodle, right? Right. If you look at if we were to go back to lecture series number 13, for instance, look at the views, right? Pay particular attention to lecture series number 13, the staff tag number 13 here. 40, 29, 31. On this one, only 18 people played it back, and you know, likelihood maybe there are some people that were playing it back maybe 3 or 4 times, right? You know, very, very sad. Very, very, very sad, actually. But anyway, on with it. Obviously, because these 2 pictures are still, they're still bad. Don't expect this distribution to be that good, right? Still don't have the no bell curve that we're expecting here, right? This thing, I keep saying this thing is supposed to be skewed somewhere at the middle here. It's not the case, right? The vast majority of people are literally failing the quizzes. Don't know why, right? Probably just not studying anyway. Now, in terms of like our leaderboard, right? Those that performed relatively okayish. I'm saying relatively okayish here because the highest score is a C+. I don't understand, right? It's a C+, 57.5%. I don't know. Anyway, I just realized that the solutions, even though the solutions are embedded in the feedback, I haven't yet exported the solutions. I will export the solutions immediately after this interaction, or at least a couple of hours after this interaction, because I'm attending another session afterwards. And then maybe in one of our weekend slot, maybe we can revise the quiz or something. Maybe we can revise the quiz, maybe on Friday or over the weekend, on Saturday or something, just so we're on the same page, right? It appears a lot of people are having problems with the last 2 questions, the calculations. Very straightforward things, but still, it's a problem. And in fact, those 2 problems were extracted from some of the examples that were given in class. The only difference was the time frame, right, within which the backups were done, and then also the sizes of the payloads, the daily payloads, right, the daily snapshots. Everything else was the same, right? It's like they're telling you 1 plus x is equal to 2, or 1 plus 1 is equal to 2, 1 plus or 2 plus v is equal to 4. What is v or something? And people are failing, right? I don't know. Anyway, so just to remind us that we have class on Saturday and Sunday, 17 hours, both days, right? I've already sent out invitations, right? URLs for Google Meet. And then we have a quiz on Tuesday, right? The quiz is going to be based on, I did send out email to that effect, but the quiz is going to be based on conversions, right? So the first bit of this lecture series the part that involves the conversions from one number system into the other. And I also did mention that it's going to cover everything all the way up to, if you've downloaded the current version of the slides, so the slides Lighton is using right now, it's number 16, it will be all the way up to, wow, it will be all the way up to 160. It will be all the way up to slide number, I don't know now, all the way up to, the quiz is going to cover everything up to, before we start the basic arithmetic operations associated with binary numbers. So that will be all the way up to slide number 163, right? So everything we've covered, that will cover until slide number 163. And you notice that 2 other quizzes have already been set up, right? So this quiz number 13 is going to be based on binary addition, multiplication, and division, and then quiz number 14 is going to be based on signed integers, unsigned and signed integers, but we'll get to that when we'll cross the bridge when we get there. All right. So prepare, right? Quiz on the 6th, which is a Tuesday. And then also we have class next weekend as well, this weekend and next weekend, right, to catch up on lost time. So this is what I was talking about here. Quiz number 12 is essentially just going to be based on, centered around number conversions, right? Very trivial, probably one of the simplest quizzes we ever write anyways. All right, unless if there are any questions, we continue our discussion. And we immediately transition into the discussion of base 2, the binary number system. Right. So we've. Can you still hear me? By the way, it's all quiet on the other side there.
Yes, we can. Yes, sir.
Yes.
Yes, sir.
Thank you very much. Great. A second there, I thought maybe I'd lost connection or something. All right. So we've been mentioning, right, for I think from the onset that computers work or they data, so far as computers are concerned, is represented as ones and zeros, right? And we know that this notion of ones and zeros is nothing more than an abstraction. Essentially, when we make reference to these ones and zeros, we're implicitly making reference to the flow of electricity within the circuitry, right? Within the various components that are composed of the circuitry. So typically, a 1 would probably represent flow of electricity, right? Or sometimes a 1 will represent a high voltage and then a 0 will be a low voltage, right? And so abstracting the flow of electricity, the flow of electric current by representing that flow in terms of ones and zeros makes it a lot easier for us to understand what's happening behind the scenes, right? And so enter the world of base 2, or binary representation, so-called ones and zeros, right? I just thought I would again remind us, this might not come out very, very soon, but it will come out. It has come out before. This whole notion that a byte, which is the smallest unit of data representation, is nothing more than the equivalent of 8 bits, right? So 1 byte is equal to 8 bits, right? Just putting it out there. And so we'll go straight to the conversions, right? So we are essentially going to look at decimal to binary conversion, binary to decimal, hexadecimal to binary, and binary to hexadecimal. And then we'd have completed the conversions that are involved insofar as the 3 bases we are mostly concerned with: hexadecimal, binary, and decimal, or base 16, base 10, and base 2, right? So we want to be able to convert from either one of these bases into the equivalent one, or equivalent desired one. So converting to binary from decimal is pretty trivial, really. Trivial because it turns out that we take advantage of the same process we were using when we were converting from decimal to hexadecimal. And so what you do is you repeatedly divide, right? So you repeatedly divide the decimal number that you want to convert into base 2, and you repeatedly divide it by 2. So the process is you set the number, the decimal number, as a quotient, and then the divisor is going to be the 2, obviously. So you divide the number by 2, and then you take note of the result after dividing the number by 2 and the remainder. The result will become the quotient, and then you divide the quotient by 2. You take note of the result and keep track of the remainder, and then you go through a loop until you get to a stage where the quotient or the result is going to be 0. And notice here, I mean, the heuristic is quite simple, really, right? Repeatedly divide, get a number x, divide by 2, get the whole number part after dividing x by 2, take note of the remainder, divide the result after dividing x by 2, take note of the remainder until the result is 0. And then same process as the conversion from decimal to hexadecimal, you represent your answer, which is composed of the remainder, by beginning with the most significant number, right, the least significant number. So bottom up, right, bottom up. And we look at examples just now. All right, so very basic example. We start 18, right? So we want to convert 18 base 10 into its equivalent representation in base 2. So we are saying that we repeatedly divide. We start by dividing the decimal representation, which is 18 by 2. We keep track of the result. In this case, the result is going to be under the Q column, which the Q is nothing more than a quotient, right? So, or you can view this as a result, and then the R is a remainder or something. So divide 18 by 2. The answer is obviously 9. We have no remainder, right? We divide 9 by 2. We know that it's 4. The remainder is 1, right? So 9 divided by 2 is 4. The remainder is 1. We divide 4 by 2. We get 2. The remainder, there's no remainder there, so 0. Please take note of what's the column R here. We divide 2 by 2. We know that the answer is 1. The remainder is 0. And then when we divide 1 by 2, it can't, right? Or rather, it's 0. The remainder is 1. For us to get the answer, obviously, we start with the most significant bit. The most significant bit is the last one here, the one at the bottom, right? So the answer will be 10010, right? So what we're saying is 18 base 10 is equal to 10010 base 2, right? And then would have converted. It's not that hard. And perhaps, and I would like to think, not perhaps, I would like to think, if you are to compare converting a decimal number to binary with converting the decimal number to hexadecimal, you realize that converting from decimal to binary is probably the easiest, because the remainder is either going to be 0 or 1. Do you understand this? Now, yeah? Is that not true?
True, sir.
Yeah, I know. Yeah, so here's the thing, right? I mean, when you're dealing with base 16 here, you can have a remainder of 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, remainder of 10, 11, 12, 13, 14, or 15, right? So you can have the remainders, as you're repeatedly dividing a number, can be either one of these 16 symbols. But when you're dealing with base 2, it's either one of the 2 symbols, right? And we have 2 symbols. The symbol we call 0, not a 0, it's a symbol. I guess the symbol is called 0, so it's a 0, right? It's a 0 or a 1, yeah? Which makes it relatively easy to actually convert from decimal to binary. It's not that hard. Is this making sense? What if we wanted to divide the year 2020, COVID-19 now, right, into the equivalent base 2? Same process, right? What you will notice, though, is that because this is a relatively small decimal number, converting to base 2 is trivial, right? But when you start dealing with relatively large decimal numbers, the process is a bit error prone, so you want to be very careful, right? As you are subtracting to get the remainder, for instance, you want to make sure that you're doing the right thing. Otherwise, you end up with the wrong answer, right? So 2020, right? Same process. What we do is we repeatedly divide. We divide the quotient or the decimal number we want to convert to base 2 by 2. So 2020 by 2 is 1010, there's no remainder, so it's 0. When we divide 1010 by 2, we get 505, the remainder is 0. But when we divide 502 by 2, we'll have a remainder of 1, right? The result is 252, the remainder is 1. So you notice, you go through the same process where you repeatedly divide by 2. So 252 by 2 is 126, remainder 0. 126 by 2 is 63, the remainder is 0. We divide 63 by 2, it's 31, the remainder is 1. We divide 31 by 2, the answer is 15, the remainder is 1. We divide 15 by 2, the answer is 7, the remainder is 1. 7 by 2 is 3, right? The remainder is 1, and then 3 by 2 is 1, the remainder is 1. And then when you divide 1 by 2, it's 0, right? Because it can't. Also, Miss Banda told us, right? So the remainder is 0, and then the answer is 0, and then the remainder is 1. Again, the heuristic tells us that we stop once we get a result of 0. And then we rearrange these remainders, the stream of 1s and 0s, from bottom to the top, right? If you're using this method, right? And then you notice that the answer is going to be that 1 1 1 1 1 1 0 0 1 0 0, right? And if it's in the exam, obviously what you would do is you would get your calculator or something, and then you confirm, right? Is 2020 there's 2 the equivalent of 1 1 1 1 1 1 0 0 1 0 0, and it is, right? Give me a second. I think I'm running out of battery power here. I need to just connect. I apologize for that. I need to connect my computer. There we go. I didn't notice it wasn't plugged into the power socket. All right. Is this making sense? It's not. Is this making sense?
Yes, sir.
Yeah. Anyway.
Yes.
At this point, right? What if somebody asked you, "Can you convert what is?" And I know what you're going to say, but we haven't done that yet. What if f into binary? I think we should be able to do this, right? What is the binary representation of this? Like simple. I mean, we'll do this, but you probably the easiest thing is to go from hex to decimal. You know this is 15, and then you repeatedly divide your 15 by 2, right? So where you have your 15, then you say 15 by 2. The answer is 7. Remainder is 1, and then 7 by this is 3. Remainder 1. 2 into 3 is 1. Remainder 1. 2 into this is 0. Remainder 1, right? Or something like that. So we see that the answer is 1 2 3 4. Stream of 4s, right? 4 1s essentially. Right? So these are things to think about.
Sir,
yes, sir.
Here when converting from hex to binary, you don't have to go through the decimal, as in you don't have to go through converting the 15 to decimal, then going to binary.
Well, I mean, you implicitly, well, there's a method, we're going to look at that. There's a method that will provide you with the illusion that you don't have to, right? If you memorize the table, we're going to look at that table. But if you notice what I've done here, I went from F hexadecimal to 15 in decimal, right? Did you notice this? This is 15 decimal.
Oh, yes.
Yeah.
Yes.
And then I was
Yes,
converting this 15 to binary, which is like 4 and 1 2 3 4, right? But I mean, so this shouldn't really be that difficult. Except the only trick here is you want to make sure that the confusion that most people have is one where when you are repeatedly dividing, right? Let's say someone tells you to say convert this IP address, for instance, and I think it's probably one of the examples we had in the exam or the test last year or the year before or something. So you are told, can you convert this dotted decimal representation of Lighton's IP address into its equivalent dotted binary representation? The mistake that most people will have is when you're repeatedly dividing by 2 here. If you just make one small little mistake, the final answer will be wrong, right? So you just want to make sure, right, that you're doing the right thing here. What is 0 base 10 in, what is 0 base 10 in base 2? This is interesting. What is the answer?
0.
Yeah, you just repeatedly divide 0 by 2, right? Which is just going to be 0. 0 divided by 2, it's 0, remainder 0, right? So 0. Anyway, that was nice, I guess, you know, it's not that hard, but all right, but it turns out, right, and I guess there's another way of looking at this conversion. There's another method.
Sir,
Yes, sir.
what's happened in the case of where the remainder is more than 1?
It can't be more than 1 when you're dividing by 2.
Okay, thank you very much.
Yeah, it's not possible. Right, okay. Good stuff. What would be interesting, what you should be thinking about here is, I just want to put it out there again, that our discussion of these mathematical operations, this part where we're discussing how a computer performs operations, mathematical operations, we're restricting our discussion. I don't know if I've mentioned this before, but we are restricting our discussions to integer numbers, right? Next year, we are leaving it up to whoever is going to be teaching you computational maths, whatever they call it, I don't know, for them to introduce you to floating point numbers or other doubles, right? So once we start looking at MIPS assembler, for instance, or once we start playing around with QT-Spin or these other simulators that are out there, MIPS simulators, you notice that as you're playing around with the two, you notice that there are floating point registers that you have access to, right? So these are registers that will enable you to compute values down to single precision or double precision. You discuss these things like decimal points and whatnot in computational maths. Our discussion is solely restricted to integer numbers. Just want to put it out there in case people are going to be wondering, whoa, but what happened here? We're restricting our discussion to just integer values. Right? Okay, good stuff. So it turns out that there's this other method, right? And I know there's probably other methods out there, especially the math miners will probably know of far more sophisticated methods. It would be nice if you could share your thoughts maybe once we are done with this method. If you know of another method that you can use to do the conversions from the different bases to equivalent other bases, right? Or desired bases. So it turns out that there's this method they call, it's called the greatest powers of 2 method, right? Or you can call it the greatest powers of 2 method. And the idea behind this method is, as opposed to you repeatedly dividing the number by 2, what you do is you repeatedly subtract the greatest power of 2 that is less than or equal to the number that you are working with at that point in time, the decimal number you're working with at that point in time. All right, so the only thing you have to do when you're using this method, if you do decide to adopt this method yourself, is perhaps on a plain piece of paper, you jot down the greatest powers of 2 from 0 all the way up to whatever maximum or something, or all the way up to the number that is equal to or less than the number you're working with or something, right? Right, so what we're going to do is just walk through some examples to showcase exactly how this works, right? So everything's centered around the powers of 2. So these things we have here are the ones we're going to be working with. If you're not familiar with this method, you notice that perhaps it might be a method you might want to adopt going forward, right? As you are familiarizing yourself with computations, right? The way a computer performs its computations. Right, so our same example of 18 base 10, what we're saying is for us to use this method of greatest powers of 2, we find the greatest power of 2 that is less or equal to 18. If we're converting 18, think about this for a second. We're converting 18 base 10. What we need to find is we need to find the greatest power of 2 that is less or equal to 18. So 2 to the power 0, 2 to the power 1, 2 to the power 3, 2 to the power 4, 2 to the power, well, 2 to the power 0 obviously is, it's not the greatest power of 2 that is less or equal to 18, right? So you go all the way, 2 to the power 1, 2 to the power 0, 2 to the power 1, 2 to the power 3, 2 to the power 4. You notice that the maximum power of 2 that will result into a number that is less or equal to 18 is 2 to the power 4. Why? Because 2 to the power 4 gives you 16. 2 to the power 5 will give you 32. 32 is greater than 18. 2 to the power 3 will give you 8. 8 is less than 16, which is less than 18. So you want to get the maximum, the greatest power of 2 that is less or equal to 18 in this case, which is 2 to the power 4, right? So we take note of 2 to the power 4 here, right? Please pay particular attention to what's happening on the greatest power column, right? So this bit here, and my thing is misbehaving. Please pay particular attention to what's happening here, right? So we subtract the result after evaluating the greatest power of 2. So 2 to the power 4 is 16. So we subtract 16 from 18. We will get 2. And then from 2, we find the greatest power of 2 that is less or equal to 2. Again, if I refer to this table, the greatest power of 2 that is less or equal to 2, you notice that is going to be 2 to the power 1, because 2 to the power 1 will give you 2. 2 is less or equal to 2, right? Because 2 is equal to 2. So 2 is less or equal to 2. We can't use 2 to the power 4 because 4 is not less or equal to 2. It's actually greater than 2. We can't use 2 to the power 0 because the answer is 1. 1 is less than 2, right? Right, so we get to this stage, and then after you do this, you subtract after evaluating the greatest power of 2, you subtract it from the result, right? Here, which is 2 minus 2, it will give you 0. And the heuristic again stops once you get the 0. Afterwards, what you do is you align, right? You arrange these powers of 2 from the maximum all the way up to 2 to the power 0 in order, right? So in this case, it will be 2 to the power 4, 2 to the power 3, 2 to the power 2, 2 to the power 1, 2 to the power 0, right? So this is what you do. You arrange them like so. And then on placeholders where you use these greatest powers of 2, you put a 1. Everywhere else, you just put a 0. You understand? So you notice that these portions that are highlighted in red here correspond with our greatest powers of 2 that we are working with. In this case, this corresponds to that. And then the 2 to the power 1 corresponds with this. And then the answer is obviously going to be 1, 0, 0, 1, 0. And then you're done, right? I think this is probably the easiest. I have no idea or no clue what you guys think. So you see that 18 power 10 is equal to 1, 0, 0, 1, 0. Is this making sense?
Yes, sir.
Yeah,
You need to, can you kindly go over it, sir? The one to do with the powers.
Yeah,
Yes,
so
sir.
there's another example actually. So maybe let's do the other example, and then we'll play around with some other example to try and reinforce this so that it sinks in. If I were you, right? As we are playing around with different methods, and I'm sure you come across other methods in literature or as you're reading up online, you want to make sure that you understand all the different methods and then decide on which method you're going to adopt, right? And familiarize yourself with that method. Do you understand this? So anyways, back to our other example of 2020, the year of the COVID, right? Let's say we want to convert 2020 base 10 to base 2 using the greatest powers of 2 method. Simple process, we first of all identify the greatest power of 2, which is less or equal to 2020 or 2020. If we go to observe, if we come here and we identify the greatest powers of 2, right? You'll notice that 0, 1, sorry about that, I just have to open a new worksheet here. Now, it's a good thing we're doing this in spreadsheet applications with Dr. Mwalimu, right? Mr. Mwalimu, sorry. So we start with 0, Okay, let's say we are working with these greatest powers of 2, right? What we're saying is that we want to identify 2 to power. We want to identify, if we are evaluating 2020, observe, the thing we are wanting to evaluate is 2020, yeah? Merge this, like Mr. Mahoney is teaching us, right? Let's merge the cells. All right, so we are evaluating this, right? Like we're being taught in special applications. Using the greatest powers of 2 method. Oh, I've reached the maximum, I suppose. I don't know. Okay, I didn't know that. It's 400%. I had no idea it was 400%. Okay. So you notice 2 to power 0 is 1, 2 to power 1 is 2, all the way up to here. We can stretch this further, right? 2 to power, let's say all the way up to here, up to power 10, I suppose. You notice that as we are stretching the powers of 2, this is what we have. We can stretch it further and I guess just have maybe all the way up to 2 to power 12, just so people have a reference point. And what you will notice here is that if you look at 2020, the greatest power of 2 that is less or equal to 20 is 1024. It cannot be 2048 because 2048 is greater than 2020. It can't be 512 because 512 is less than this, the immediate power of 2 that follows it, right? So we pick 1020, which is 2 to power 10, right? Greatest power of 2. Then what we do once we identify the greatest power of 10 is we evaluate that greatest power of 2. Could you please mute your microphone? I don't know who you are. Please. Thank you. Right. So 2 to power 10 is 1024. We subtract 1024 from 2020, we will get 996. We find the greatest power of 2 that is less or equal to 996. If you go to this table, which greatest power of 2 is less or equal to 996? You notice that it's here, right? So we pick that, which is 2 to power 9, right? So we take note of the 2 to power 9. We evaluate 2 to power 9, we find that it's 512. We subtract 512 from 996. We find 484. We find the greatest power of 2, which is less or equal to 448. If you come here, which number is less or equal to 448? You notice that it's here, right? It can't be this because this is greater. It can't be this is far less than this. So it's 2 to power 8. We take note of 2 to power 8, and then we subtract 256, which is the result of raising 2 to power to 8. We subtract 256 from 484, we get 228, right? We find the greatest power of 2. That will give us a number that is less or equal to 228. You notice that it will be 2 to power 7 because we need this number here, 128, right? So we subtract 128 from 228, right? So we subtract 128 from 228, we get 100. And then we find the greatest power of 2 that is less or equal to 100. Go back to our table, you notice that it has to be 2 to power 6 or 64, right? So we subtract 64 from 100, we get 36. Then we find the greatest power of 2 that is less or equal to 36, and you notice that it has to be 2 to power 5 because it will give us 32. We subtract 32 from 36, we get 4. Then we find the greatest power of 2, which is less or equal to 4. It turns out it has to be 2 to power 2 because 2 to power 2 will give you 4, right? 4 is less or equal to 4, right? So you take note of that, and then you subtract 4 from 4, you get a 0. At which point the heuristic stops, right? You stop repeatedly dividing because you've converged, right? You get to 0, that's it. And then you align these powers of 2, left to right, beginning the highest power of 2. Yeah? Left to right, beginning the highest power of 2, all the way up to the least power of 2. So 2 to power 10 up to 2 to power 0. 2 to power 10 up to 2 to power 0. And then you provide a mapping, you place a 1 against each of the greatest powers of 2 that you utilized as you were repeatedly subtracting the powers of 2 here. So you notice that these things highlighted in red here correspond with these things we have here. This corresponds to this. Is this making sense?
Sir,
Yes,
so at the end
yes,
of
it
each
is.
calculation, doesn't mean that at the end of each calculation, you're supposed to make a table and then put one at the end of to the equivalence of the powers you just calculated.
No, not really. I mean, if you can think of a better way of representing these things here, then that's fine. You don't have to draw a table. If you want, right? Once you get to this stage here, observe. Once you get to this stage here, you know that you're supposed to have 0, 1, 2, 3, 4, 5. If you can form a mental picture of the different placeholders that you're going to associate these greatest powers of 2, then that's fine. You don't have to draw this table. But when you're getting started, for you to understand this method, you'll probably be better off you'll be better off drawing a table similar to this. It doesn't have to be a table, right? It'll be just a stream of powers of 2. Let's say you have, you're computing your answer, and what you do is you just write them down. You say you have 10, 9, 8, 7, 6, 5, 4. It doesn't have to be a table. And then you start placing 1s and 0s against applicable powers of 2. So you only place 1s on powers of 2 that you've used during your computation here. I don't know if that answers your question, but
Yes, sir, it does.
is this making sense? Is this okay? Is this confusing?
Yes, sir.
Okay. Then, so the question then is, if this is clear, the question then is, how exactly do we get to convert from binary to decimal? Well, it turns out that we can take advantage of the same methods that we use when we're converting from hexadecimal to decimal. What do? We make use of the radix for the base that we're working with. In this case, is base 2. And then you repeatedly multiply, right? I don't know if you remember what we were doing last time. So you repeatedly multiply the bits that you have, right? You have a binary number representation. You repeatedly multiply the values in that base 2 number, the symbols in that base 2 number by the equivalent radix. And we have an example to showcase this. And then at the end, obviously, you get the sum of products, right? Simple heuristic. I guess it will make sense if we look at an example. Let's say we want to convert 1,001,01. No, it is not 100,101. It's 1,001,01, right? Base 2. So we want to convert that to base 10. What do? We arrange these bits or these symbols associated with the base 2 number left to right, the way they're presented like so. And then we identify the corresponding powers of 2 associated with them, beginning 2 to the power 0, right? Right to left. So 2 to the power 0, 2 to the power 1, 2 to the power 2, 2 to the power 3, power 4, power 5, right? So when you have a number like 1,001,01, it turns out that this is what's called the least significant bit because it has the lowest value, right? Least significant bit, most significant bit, right? In this case. So we are arranging them left to right. Because this is the most significant bit, it's supposed to be associated with the highest power of 2. Yeah? All right, so we get powers of 2 like so, and then we evaluate the the powers of 2, right? So 2 to the power 0, 2 to the power 1, 2 to the power 2, power 3, power 4, power 5. We evaluate them, and then we multiply the symbol, the base 2 symbol, with the evaluated power of 2, right? So in this case, it will be 1 times 32. So 1 times, I don't know where this is. 1 times 32, this is missing here. I do apologize here. It might be a bit confusing here, but bear with me. But I don't think it's confusing. So 1 times 32 is 32, right? 0 times 16 is 0. 0 times 8 is 0. 1 times 4 is 4. That's a horrible looking 4, but you know it's 4. 0 times 2 is 0. I find it hard writing with my mouse, right? 1 times 1 is 1. Now, this is the reason why I omitted these other numbers when I was adding these. I just omitted anything with a 0. You know, any number times 0 is a 0, right? So you just concentrate on the ones here, right? So 1 times 2, 1 times 4, 1 times 1. And then you add them up, right? So 32 plus 4 plus 1, you get 37. And it's not that hard, right? So you get the sum of products. Is this making sense? So you notice that the only difference if we were to compare the conversion from hexadecimal to decimal, for instance, is that in the hexadecimal to decimal conversion, there was an additional step where we had to get the corresponding equivalent symbol, decimal symbol, for all of those hexadecimal symbols from A up to F. Right, so we had to get a representation of A as being 10, B as being 11, F as being 15. In this case, we don't have that particular step really. All we do is we do a direct multiplication between the evaluated power of 2 and the bit associated with the binary number you're converting. Is this making sense?
Yes, sir.
Yeah, I thought so too. So this is what you have here, right? So this is the actual process. Oh, there we go. This is the process I was looking for here. I swapped the slides, I guess. I'll have to change it at some stage. Don't know why, but so this is the step I was looking for, where you multiply each of these symbols by the evaluated power of 2, right? So 1 times 32, 0 times 16, 0 times 8, 1 times 4, 0 times 2, 1 times 1, and then you get the sum of products, right? So you add all of these resulting values. And then you get 100,101. Sorry, you get 37. There's 10. Is this making sense?
Yes, it is, sir.
So there's a thing. Yeah, thank you.
Yes,
I thought so. So there's a thing, right? Let's look at a slightly larger number, right? And we know this is a slightly larger number is because if you look at the mapping of if you look at this from the perspective of least significant bit to most significant bit here, you notice that 2 to the power 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So whatever number we're going to get here it will have to be greater than 2 to the power 10. Do you understand? Because it's greater than 2 to the power 10, we know that the larger the number of bits we're working with, the larger the magnitude of the equivalent base 10 number that you're working with, right? So 2 to the power, I guess, I don't know, 2 to the power 10. We know that the number we're working with is going to be more than 1024, right? So same process, really. Oh, I have a presentation I have to attend, sorry. So what we do is we first of all identify the equivalent. So you lay down this base 2 number, right? Left to right, the way it's presented like so. And then you identify the powers of 2 associated with each one of these bits in this number. So you notice that it's 2 to the power 0 all the way up to 2 to the power 10. And then you evaluate the powers of 2, right? 1, 2, 4, 8, 16, 32, 64, 128, 256, 512, 1024. And then you just multiply the bits here, 1 by the evaluated powers of 2, right? And then this is what you have. And then you get the sum of products. You add them up. And then that's it. It's not that hard, yeah? Guys, I want us to part ways right here. We shall continue this conversation on Friday. I do believe on Friday we should be done with binary to hexadecimal and then hexadecimal to binary, which is good actually, because once we are done with, I don't know, binary to, once we are done with this, we can immediately start the addition, binary addition, binary multiplication, and binary subtraction, binary division, right? Which I'm hoping we can finalize during the weekend, right? So on Saturday and on Sunday, and then on Monday we can maybe start looking at signed and unsigned integers to see how these are represented by a computer. And it is usually modern day computers will do this using 2's complement, but we'll look at the different techniques, possible techniques that are available for us to use. And in fact, some of these techniques were used in the past, right? So things like sign magnitude, for instance, or one's complement. And interesting conversation or interesting things will come up, like the disadvantages of representing binary numbers using one's complement as opposed to two's complement, for instance. So anyways, I'll see you when you see me, which is day after tomorrow. Thanks a lot. I do encourage you to download these slides because they've been updated, please. Yes, sir.
I was asking if you're going to upload the recording right away so that I can go through it.
Oh, yes, not right away, but as soon as the rendering is done, turns out I go through the process of where I have to, I move this to YouTube. I don't share this using Drive, which I don't like doing it using Drive. Maybe I should start doing it, I don't know. But I will upload it today, yes.
Sir.
All right,
Sir,
thank you.
Do you mind making a walkthrough for the last quiz?
Yes, I mind because
So
I'm rushing for another appointment. So I mind. I did mention that would look at the quiz either on Friday or on Saturday.
Sir.
Yes, sir.
Would you possibly give some of us who never wrote the quiz a makeup because we are deregistered? I'm not the only one, by the way. There are many other people.
Yes, you'll be given a makeup.
Oh, thank you, sir.
Yeah. All right. So the thing with the makeup is that the registration thing is it can be a bit it's messing up a lot of things. So what we're doing is we are probably going to, once we get to a stage where a number of people have re-registered, that's when we'll organize makeups. Because it turns out some of your colleagues actually missed quiz number 10 and quiz number 9 because they were deregistered at that point in time, right? So we are thinking that maybe we'll give you a chance until maybe 2 weeks time when we'll start having those makeups. All right. Good luck, and I hope you get into a stage where you can start preparing for the quiz on Tuesday. Bye bye. Thank you.
Bye, sir.
Very exciting. Guys,